if you're comfortable and all that. No, if you want to, I don't know, you can, it's your choice. नहीं ये ब्लैक वायरस नहीं लाना, इसको चार्जिंग कर दी नहीं। नो मैम इसकी हाँ नहीं कोई नहीं क्या आती नो मैम यहाँ से ठीक हो। अच्छा ये असद है और किस किस ने ज्वाइन किया हमें? तहरीम एंड असद।
अस्सलाम वालेकुम मैम। अस्सलाम वालेकुम मैम।
वालेकुम सलाम तहरीम, क्या हाल है तुम्हारा?
जी मैम आई एम गुड बेटर।
अच्छा ये पावर कहाँ लगेगी? ये नहीं लगेगी है ना, मुश्किल है, तार छोटी है। फिर बाकी सारी चीजें हिल जाएंगी। कुर्सी का कुर्सी फिर तुम भी चल सकते हो नहीं मैं जिस चीज की वजह से नहीं बोलता मुझे डर के हुआ है। ओह माय गॉड हम कहाँ फंस गए? तो अब हम स्पीकर नहीं लगा सकते थे, रिंग के बाद इतनी हल्की है उसमें। हाउ टू डू दिस? पावर कहाँ पे लगाएं? पावर बैंक भी नहीं इसके साथ लगेगा है ना। वो वाली तार छोटी है, वाली तार कहाँ से आती है? इधर से आती है। फिर हम स्पीकर भी लगा सकते थे, रिंग की आवाज कैसे सुनेंगे? असद एडमिट, तहरीम एडमिट। अच्छा पार्टिसिपेंट्स हो गए हैं हमारे पास। शर्जील नहीं अभी आया। बात सुनो, मेरी बात सुनो दुर्गाना। इफ यू डोंट फील डिस्टर्ब, तुम्हें थोड़ा सा डिस्टर्ब कर, अगर मैं इसको उधर लगा लूं है स्पीकर के साथ ये ऑन करके देखो। मैं उधर कर दूंगी, हाँ मैं इधर बैठ जाती हूँ। I'll sit on this side, ठीक है? Sorry for the disturbance. आज यू somehow हम लोग इतने बिजी हैं, आप अपना प्रोजेक्टर जहाँ पर वहीं लगा लो, मुझे एक्सटेंशन उधर लगा दो बस। और रामीना अपने साथ टेबल पे होगा। जैसे आप नहीं स्पीकर से है ना, स्पीकर छोटे हैं वही तो सारा मसला। अब हम ठीक है? Where is the this? शोर क्यों आ रहा है? ये शोर क्यों आता है इसके बाद?
हेलो मैम।
हेलो बेटा, लेकिन इसमें क्यों ये आवाज आ रही है? चलो I guess this is because of the proximity of the ये काटते हैं तो बंद हो जाती है आवाज। हाँ लैपटॉप चार्ज नहीं होगा, अब हो रहा है, अब भी नहीं हो रहा, बहुत सेंसिटिव है। बस 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 अब ठीक है। अच्छा, हेलो हेलो
Hi, ma'am.
Asad, I am testing the sound. Okay, so please help me test it. Okay,
Yes, ma'am. I'm here. Asad 123.
I am just a moment. Let me see how I can do this. अब ठीक है? Asad, will you say something?
Yes, my name is Asad, and I am
Just okay.
online on Zoom. So yeah.
Okay, so I think we can hear each other, right?
Yes, ma'am.
Everything's good?
Yes, ma'am. Until now.
Okay, Sharjeel, can you hear us?
Yes, ma'am. I can hear you.
Okay, Tahreen, can you hear us?
Yes, ma'am.
Everything's okay?
Yes, ma'am.
Sharjeel, you have your presentation you will be sharing with us after Durdana. ठीक है?
Sure, ma'am. I'm ready.
So ready? Tahreen? Tahreen? Hello,
Yes, ma'am.
बेटा आपके पास
Yes, ma'am.
do you have your presentation?
Yes, ma'am.
After Sharjeel, you can present, okay?
Okay, ma'am. Ma'am, I have also sent the recorded presentation on your email as well.
Okay, thank you so much. I want you to present
Okay, ma'am.
this also so that we can have a discussion, okay? Just like a
Okay, ma'am. Okay. Okay, ma'am. Okay.
तुम्हारी मैं डाउनलोड करके शेयर करूँ। Let's do it. Let me handle it because वो उसमें फिर chat के question answers भी and otherwise भी let's do it like that. ठीक है? I have your presentation, right? Let me download yours. अब एमन को देख लो हैं उसके नंबर कटेंगे उसको बता दो ठीक है अच्छा so today is the 18th of Feb and this is Durdana and I'm going to share her presentation okay अच्छा आप बताओ तुम लाइटिंग तुम्हारे हिसाब से ठीक है do you want to switch it off या on या बताओ तुम्हारे ख्याल से क्या चाहिए थोड़ा ऑफ कर लेंगे तो ये ज़्यादा अच्छा हो जाएगा चलो फिर इसकी शक्ल नहीं नजर आएगी ठीक है we'll see the presentation will not see her ओके वो मुझे पता है मैंने अपना भी एक दफा ऐसे किया था तो वो यू कैन नॉट सी द पर्सन वो फिर इसी पे फोकस करता है चलो जी लेट्स सी आई एम गोइंग टू शेयर विद एवरीवन this one okay share okay so go ahead you can start do you want to use a mic I have a mic if you want लेकिन तुम फंस जाओगे बता रहे हाँ yes okay so speak loud so that we can hear you Good evening, I'm Dana, and today's topic of my presentation is the force between nucleons. So, for some familiar properties, we have been talking and listening and hearing about the strong nuclear force and weak nuclear force, and generally the nuclear forces since we have started studying this force. So, what is actually the strong nuclear force? Some of the familiar properties which we know by general knowledge are that it is a very strong force, like the name suggests. Also, it has does is it combines, it makes the protons inside the nucleus stay close to each other. And to do so, it has to like overcome the electromagnetic potential which it has. So like if it was not for the strong force, the Coulomb repulsion between the two protons would be about 20 pounds, which is around 9 kilograms. And it has been if it has been left as is, the protons would spring about at a speed of 8,000 miles per second from each other. Next we have like this is a force that keeps the nucleus together, and in a very short range force, as you can see that the radius of the nucleus is very small, and there is no evidence that the nuclear force interacts with other particles like the charged particles like electron or other fundamental particles, except for quarks or the ones that are present in the nucleus. So going so, like, to further investigate what the course actually dictates is we would study the neutron, which is the nucleus of deuterium. Deuterium is a an isotope of the hydrogen atom with one proton and one neutron. So, to study this, we have a neutron and a simple neutron system of two neutrons. And we have studied in our course that the average binding energy for neutron is about 7 to 8 MeV. But while experimentation, we have realized that the binding energy of neutron is merely at 3.2 MeV, which is why we can say that neutron is a very weakly bound system in terms of the neutron or the nucleus. Next, so to study the the neutron, we saw we took help from the quantum mechanics, and we actually put our the wave functions of the neutrons, we captured them in a potential well, so they would remain there, and we calculated the radius and the potential and the wave functions for the neutrons. So here in the diagram we have the potential well of the potential minus V naught and with the reference point 0, and small r represents the separation between the neutrons, and capital R is actually the radius of the neutron, of the nucleus, sorry. And by doing this calculation and solving the time independent Schrodinger equation in the radial quantity, we get these two expressions for u r. One is sine function and another is the negative exponential function. And correspondingly, you get this relation between the wave numbers of the corresponding eigenfunctions. And further solving these expressions, we get the potential value to be 35 megaelectrons, and the radius of the deuteron to be 1.2 centimeters. This indicates that the wave function, if it was not so, the wave function would not go as smoothly. You can see that in the start, it starts as sine function, but it goes smoothly with negative or exponential function with a 2.1, where the radius is 2.1 centimeters. What does this entail? It entails that if it was not this particular value, the nuclear force would be weak. It would be not as strong, and our wave function would actually escape the potential level. Which means that we would not have a bound state of neutrons. We would not have nucleus as we have now, and that would the universe as we know would not exist because we won't have a bound state of the nucleus. So that's about it about the neutron part, and some properties of neutron that we get are its constituents. It constitutes of one proton and one neutron. Its mass is about 2.0 mu, or which is 1876 megaelectron volts, which is very high. And then its binding energy is near 2.2 megaelectron volts. It has total angular momentum of one. It has a even parity because we have a neutron and a proton, and we are fermions with intrinsic parity, intrinsic even parity. But what we get here is that the magnetic dipole moment and electric quadrupole movement does not match this. Earlier, when we studied the finite potential well, we took the assumption that the orbital angular momentum is zero. So we can calculate that we can do our calculations without the bound state. But here, for the sorry. For the orbital momentum to be zero, it has a consequence that the quadrupole moment and the dipole moment should also go to zero, but it does not. That entails that the nuclear energy or the nuclear force or the force that we are studying is actually dependent on something else, and it's not just which gives us another orbital momentum value. So, like, also the Nucleon square separations for 2 centimeter, we have already talked about the radius of an atom, which is 2.1 centimeter. Next is the properties of the strong nuclear force. Computer analysis, which I just did, we can see that there is only one bound state. The only excited state of a nucleon is the unbound state, where the proton and neutron exist. And it depends on the spin of the nucleon because the quadrupole moment and the dipole moment is not vanishes. And again, the angular momentum now equals to zero. It is not the only allowed orbital angular momentum value. Equals to also exists to get the total angular momentum of one, because the spin we know is half of the proton and neutron. It could be, and they have to be parallel. So it could be negative half plus 2, which is also equal to 1. So I have not discussed the nucleon scattering, but if the direct consequences from that, the direct results we get from them is that the nuclear force has a repulsive core and it is charge independence. That means that if we have an interaction between a proton and a neutron proton or a neutron, the strong force would not discriminate amongst them. It would react, it would be applied same way to all of these. Up next is the exchange force mode. So we have looked at the strong nuclear force, like how and what properties are, but how is it actually doing what it does? How it is holding the neutron together, the nucleus together. So, like exchange force model is one of the models which explains that, and it actually attempts to answer the question that how does two particles or two objects affect each other without touching. So the answer is that it gives is that there are actually force-carrying particles that exchange between them, and through that, the force is actually acted from one object to the other. And applying this model to our current topic, the strong nuclear force, we say that actually the virtual particles, mesons are exchanged between to create this force, to create the strong nuclear force. Mesons are bosons. These are particles with spin 0 and 1, and they are positive particles with two parts and a part and an antipart. They are electrically charged or they could be neutral, and we say that in the strong nuclear interaction, the lightest of the mesons, the pi, are exchanged between the nucleons. Like I have inserted this. Find my diagram. The virtual particles are shown by the dotted line, and the particles with simple line. The line is going in the x direction in this photograph, in this picture. So these two are the examples of the reactions, the how interaction occurs. The first one is between nuclear interaction, the second one is on the high temporal uncertainty principle and the fact that we cannot measure energy and time simultaneously. Because the time here, the pions or the mesons are particles of very small lifetime, hundreds of microsecond their lifespan is. And in the end, I'm just going to say that the strong nuclear force, which we actually see here, is actually the residual strong nuclear force, which is which we see by the actually the fundamental particles which are present between the neutrons, neutron and proton, which are quarks. They interact with each other through the exchange particles that are gluons, and that's how the exchange force. That is what is actually happening inside the strong nuclear force. And that's it. Thank you. Any questions? And these are the references.
Okay, wow. Okay, so thank you, Durdana. That was nice. So now we would like to invite you for questions. So please ask your questions. Tehreem, do you have a question?
No, ma'am.
Bolo?
No, ma'am.
Yes. Shajil, do you want to ask some question? Shajil?
No, ma'am, I have no question.
No, Shajil, you have to ask a question.
Ma'am, can you hear me?
Yes, we can hear you.
I don't know why. Can you hear me, ma'am?
Yes, we can hear you.
Actually, I tried to connect my hands, but I guess they weren't connected. I don't know why. So I guess I have to go without the hand freeze. Yes, ma'am, I have no questions at all, ma'am. It was good.
Shajil, do you understand the whole topic?
Yes, ma'am.
No, Shajil, that's not possible. Tehreem?
Ma'am, my internet connection was not stable at that time. I joined
Ma'am,
two
I
times.
understood all of the topic.
Okay, so Asad, you can go ahead.
Well, as a whole, it was a very fine presentation, giving the concept of kind of a quantum field theory and explaining how a very strong force and it acts over a very short range. And she gave some very good reasons that mesons can only be stable up to a few femtometers. But yeah, there was this one question that I would. Meson is technically speaking a combination of your quarks, a kind of a quark combination that includes only two quarks. But why is that so? You need a quark and an anti-quark pair in order to make a meson, despite you having 6 more flavors of quarks at the same time.
What? I did not get the question.
A meson, by definition, is a quark combination containing 2 quarks only, right now? But why is that so in all of the mesons, especially in all of the pi mesons, or the ones that you call pion that are responsible for the strong interaction between 2 different nucleons, we only find a quark and an anti-quark pair, but not like one up quark, one down quark, or like one strange quark and one charm quark, and like one top quark and one bottom quark. Why is that so?
I have not made them, so like जिन लोगों ने इसको terminologies दिए हैं, I guess they would be able to answer that question.
I do have a slight idea that it has something to do with quantum chromodynamics, but I'm not really sure. So yeah, it's really
Related to the flavor and the thermodynamics, but I am not sure about that because I have not studied that far into it.
oh, okay.
Thank you. Any other question?
Asad?
Yes, ma'am.
Can you ask a question directly related to her presentation, because this is beyond the scope of her presentation, right?
Well, as far as the presentation is concerned, it was, I think, very complete, and she explained everything, and I do not have any kind of queries in them. So
Okay.
yeah.
Okay, good. Shajil? And Tehreem? अच्छा, Ramin? हाँ, तो फिर तो you should ask something. Okay, yes, the topic was new, yes, but it's very relevant and it's very interesting as well. And you can also see how she has explained this with the help of the potential well. And I would also relate this to the fact that, for example, Asad was explaining his topic with the help of a potential barrier. And in this case, we have a potential well, है ना? So that's interesting in that case. You can see both an application in this course. You have seen both an application of the potential barrier and the potential well. So can you please explain how we can relate this concept of potential well to the phenomena, to the topic that you explained? Loud, please.
Potential well is study or potential well means take a bounded state of the particle study whose energy are low and they can be captured in the well. So here we have the nucleus or the neutron, which we are stating, we are assuming that it is a bound state and it is a stable state. So we are taking it in Vancouver. So like it would, and we're studying whether we get the answer and whether we get the solutions that we see in the actual life, whether our mathematical calculations agree with the physical limitations or the experimentations we have done.
Okay. So your assumption is L is equal to 0. What is L?
L is the orbital angle.
Okay, of the nucleons or the nucleus?
Nucleus. Like the whole nucleus.
Yes.
So the nucleons were
That are bound.
and they orbiting and they total orbital.
Okay, and what is capital R here?
Capital R is the radius of the nucleus.
Of the nucleus. And this can also, you can also relate this topic to chapter number 3, chapter number 3, in which we were studying the properties of the nucleus. You remember? And there also we saw this R is equal to 1.2 femtometers.
Yeah, that 1.2 is 2.1.
Okay. In this one you've written 1.2. Acha. So you can check this and send me the corrected one, okay? And also, although in chapter 3, that was one of the basic chapters we did about the nucleus, it was concerned with the properties of the nucleus, but you can also, we did not do such advanced calculations in that chapter, but you can also see that these calculations relate to the properties that we studied in chapter number 3. So you see, we always start with some basic fundamental concepts, but there's a lot of advanced physics involved in that. So you can later on go into depth and explore that as you understand it better. So that's a very interesting example of how we can do this, right? Okay. Let's come here. So the concept of binding energy again is one of the very fundamental concepts of nuclear physics, and you can also see that we have an application in this case as well. So in this diagram also you've shown us the binding energy of the neutron, yes, with the dotted line. So can you please explain this?
The total potential well has taken the graph to be 35 megamoles, and the binding energy.
Okay, let me speak along with you, maybe that so that everybody can also understand. So you said that the total
potential,
the total depth of this well is 35 MeV. Okay.
So, but the binding energy which we have calculated by other experiments or
But the binding energy of the neutron that has been calculated with the help of other experiments
or the theoretical calculations
and theoretical calculations as well.
by like reactions between
Yeah, which has been explored with the help of the concept of nuclear reactions.
that is 2.2 mega electrons.
So that is 2.2 mega electron volts.
Means that the neutron is present within the well, but it's very near to the boundary of the well.
So this proves that the neutron is present within this well, but it is close to the boundary of the well.
And it was a little bit weaker,
Mhm.
and it did not contain
So if it was a little bit weaker and it did not contain,
the negative exponential function.
okay, the negative exponential and the sign function that we have in the Schrodinger equation,
Actually escape the well.
so then it would escape this well.
And we would have an unbound state.
And then this would lead to an unbound state.
So we would not have a neutron, which means we would not have fusion reactions.
So that means that there wouldn't be any neutron and hence there wouldn't be any fusion reaction. So you see this leads us to the fusion concept as well.
And like that's why that if that would have to happen, we would not have the universe as we see now.
And if we had no fusion, we would not have the universe. Wow, that was great, Durdana. That was a very good explanation. Okay, so you see, she did the maths and she also has a very good understanding of the physics and the concepts and their applications as well. So that's very interesting. Okay, so here, acha, is slide mein you've written 2.1 femtometer. Please check your slides again and you can send me if you need to make a correction, okay? So, yes, here we have the RMS separation, right? And in this table. So can you please just walk us through what is RMS separation? Okay, so again, this we also did this in chapter number 3, which was the basic properties of the nucleus itself, right? And you can see that again, this is a reference to that value. So just a moment, what's the heading of your table? Properties of a neutron. Okay, right. Let me see just a moment. Properties of a neutron. So a neutron has one proton and one neutron. This is the mass, the binding energy, the angular momentum, and so on. And then you have the RMS separation. Okay. Again, in this slide, it's interesting to point out that from the nucleon scattering, the conclusion is one, that the nuclear force has a repulsive core, and number 2, that the charge independence of the strong nuclear force. Again, I would also like to relate this again to chapter number 3, in which we also drew similar conclusions about the nucleus itself. Hannah? Yes, we concluded there also that the radius, when we were talking about the radius of a nucleus, we said that the radius of the nucleus does not depend on these factors, right? So you see how this is all very interrelated. Okay. Can you please explain this diagram?
This diagram,
Yes.
this is a Feynman diagram.
Okay, this is a Feynman diagram.
So it's actually representing a neutron proton reaction.
So this represents a neutron proton reaction, interaction.
Actually, on the x-axis, we have time.
So the x-axis has time, and the y-axis represents the distance.
Yeah. So a proton and neutron comes together and they exchange a pion.
And when a proton and a neutron come together, they exchange a pion.
Yeah, pion, like this pion is actually a neutral pion.
Okay, and this is a neutral pion.
And it is scattered at an angle with the same properties and characters. It goes into a proton.
And then the proton and the neutron scatter again after the exchange of this particle.
Yeah.
So,
Neutral particles that is being exchanged.
so a neutral particle is being exchanged in this case, and this is the exchange force model, right? Okay. Again, this is relating to the nucleons and the exchange of a pion. sorry, a meson in this case, right? And wow, that was good. That was very good. Thank you, Durdana. Okay, now for the online participants, I would disconnect the meeting, and then you can click the same link again and rejoin us for for the next presentation, which is by Shurjeel. Okay, Shurjeel?
Sure, ma'am.
Okay, so see you in the next presentation. Okay.
Okay, ma'am.
तुम 10-10 मिनट बना रही हो ना? हाँ, बिकॉज उससे बड़ी नहीं हम हैंडल कर सकते.